let's continue our discussion on the electrostatic force. We know that the electrostatic force exists between charged objects according to the experimental observations. But how to determine the magnitude and the direction of the force between charges? Coulomb's law gave us an answer. Before discussing Coulomb's law, we'll propose a model, an ideal model, point charge, which refers to a point-like object with electric charges. It has no size and no dimension. That means the charge distribution of the object could be neglected when we resolve the problems. For example, electrons and protons could be described by modeling them as point charges. By applying the torsion balance like this instrument, Charles Coulomb measured the magnitudes of the electrostatic forces. Here are two charged spheres A and B. Here is the suspended fiber. Due to the electrostatic interaction between A and B, the two spheres attract or repel each other, causing the fiber to twist through an angle. This angle is proportional to the restoring torque of the twisted fiber. So the electrostatic force between these two spheres can be obtained by measuring the angle. Since these two small spheres are treated as particles, the experimental result could be applied to the point charges. Based on Coulomb's experiments, we can generalize the properties of the electrostatic force between two stationary charged particles. The magnitude and the direction of the electrostatic force between two point charges is given by Coulomb's law. Firstly, let's examine the magnitude as expressed by this equation. The magnitude of the force is proportional to the product of the charges Q1 and Q2, and inversely proportional to the square of the distance between two charges. Here, epsilon 0 is called permittivity of free space. By applying Coulomb's law to solve the problem, please don't forget that a force is a vector quantity. You have to find both the magnitude and the direction of the force. In this equation, the vector F12 presents the force on Q2 exerted by the charge Q1. R12 hat represents a unit vector directed from Q1 towards Q2. Please look at this graph. If the charges have the same sign, the force is repulsive, so F12 should be the same direction as that of R12 hat, since the product of Q1, Q2 is positive. On the other hand, the product of Q1, Q2 is negative with the opposite signs, and the force is attractive. F12 should be opposite to that of R12. Electric forces obey Newton's third law. The force on Q1 is equal in magnitude and opposite in direction to the force on Q2, as expressed by this one. If there are two more point charges in space, how to find the net force on any one charge? The force between any pair of them is determined by the formula discussed above. Hence, the resultant force on any one charge equals the vector sum of the forces exerted by the other individual charges. For example, there are total 4 charges present. The force on the charge Q1 equals the vector sum of the forces exerted by the charges Q2, Q3, and Q4. Please note that it is the vector sum, not the algebraic sum. We must be very careful about the direction of each force. Now let me give you an example to show how to find the net force. There are two identical charge spheres as shown in the figure. The string makes angle theta with the vertical. The mass of the sphere is m, and the length of the string is l. Please calculate the magnitude of the charge on each sphere. As shown in the figure, These two spheres repel each other. This indicates that they carry charges of the same sign. Applying Newton's law, the spheres are modeled as particles in equilibrium. Let's first draw a free body diagram. The forces exerted on one sphere includes the tension from the string, the electric force from another sphere, and the gravitational force. Based on the equilibrium of the model, the net force on the left-hand sphere is equal to 0 for each component. The right-hand sphere has the same situation. We can write down the equations for each direction by applying Newton's second law, as shown here. Based on these equations, we can solve for Q. You may notice that the electric force exists between two spheres without any physical contact. How to understand the interaction between two objects in such a case? How to interact with each other without the physical contact? We'll discuss it in details next lecture.